Hey guys, this is Peter, and over the years I've learned so much from your comments and questions, but because of you guys, I'm able to call major manufacturers and get them to send me product and get them on the phone and answer some of my questions. So I've developed relationships between Proxicast, Jim, and Kevin over there have answered so many questions. I enjoy our calls so much because they have 25 years of experience. They know this stuff is inside and out. And I thought it would just be interesting for you guys to be like part of our conference call and chat about stuff. So I picked a topic, and we picked extended range, 5G and 4G, and just ask questions about that. Hey, if you enjoyed this, do give it thumbs up, and we'll do more, of course. Let us know down below what you'd like us to talk about next. We're willing to do that. And if you have questions for either Kevin or Jim or both of them, leave it in the comments below. They will be monitoring this and go ahead and answer it for us. Again, 25 years of experience. What a treat. Hey, if you do like this, do give a thumbs up. And there you go, guys. Sit back and enjoy. Hey, I'm here with Kevin and Jim from Proxicast. And I decided I get so many great questions from you guys. We would just talk to the experts and ask some of these questions. A lot of the questions are about rural internet and what we can do with it. So, how far can it go? Let's ask these guys. Tell us, guys. How far can 4G and 5G signals go?
Depends on the environment. The ideal situation where you've got a flat area, hard surface, typically you can see 10, 15, even 20 miles with special directional antennas, things like that. But I would assume, if you're within 10 miles, you should have a pretty good chance of getting a good signal. When you get into, more hilly areas or near water, it can go down significantly just because you now got to deal with line of sight issues, or if you're a very wooded area, those can all be factors, and you may need different types of equipment. For example, a directional antenna I spoke about, that works best when you have what we call clear line of sight, which is nothing between you and the tower. No trees, no buildings, no hills, just you and the tower, and it works, you think of kind of like a laser beam. It's going straight towards that tower. When you get into where there's signals bouncing around off of hills and walls and buildings, you tend to look at more or less directional antennas, either panels or even omnidirectionals, because they can pick up signals bouncing around from different places.
And Kevin, you were telling me before that some of these towers can do beam forming, and they can actually point down a Florida Turnpike or whatever. So even though you can see it, it may not be pointed at you.
Yeah, that's correct. Obviously, the carrier wants to put the signal where their paying customers are. So particularly if you're near a major interstate or a highway system, that beam's going to be designed to go parallel up and down the road. There will be some off-axis or off. The majority of it, and the way the bandwidth is allocated, it's going to be where the customers are. There's also, again, it goes back to geometry. You can see a tower, but the towers, they have what's called a down tilt, either physical or an electrical down tilt on those sector antennas where they're aiming that downwards. So if you're too far away, you can't actually hit, you're overshooting the tower. Or if you're too close, you can't get it because you're under it. And so you have to do a little bit of math to figure out, whether you can actually reach that or not.
Okay, and we also talked about how some towers put out different frequencies or different bands. And the bands that travel really far are, the lower frequency bands. So I guess you have to adjust in your mind and lower your expectations. You're not going to get gigabit speeds from a 600 megahertz signal, right?
Correct. Yeah. The higher the frequency, not only the faster the data, but the way the carriers look at it is more payload. So they can actually have more broadband in the higher frequencies. That's one of the big things about the C-band is, I forgot what the factor is, but it's like, I think it's a factor of 12 over the 700-800 band that they can carry more payload in the same, frequency spectrum.
It seems that this is a bit more complicated than just picking a band and trying to get it.
Well, actually, there's multiple things that can limit your speed. And when you're talking about rural, it's not only the speed between your device and the tower, it's the speed for the tower back to the internet. It's called the backhaul. And again, when you get into very rural locations where there's very few customers, the carriers don't want to invest in the money in putting in high-speed fiber optic. So they tend to have things like microwave backhaul, which isn't going to go at gigabit speeds. And it's a shared resource. So everybody who's connecting is sharing that same backhaul. So at different times of day, you may get different performance because there's more or less users.
You were also telling me that if you did want to get one of these lower frequencies, like 600 megahertz, that because the frequency is lower, you want to put more metal up in the sky.
Yeah, as Jim mentioned, the lower frequencies will travel further. They'll go penetrate through objects better. They'll go through the walls of your house and things like that better, trees better than that. But when it comes down to, I mean, what an antenna really is, it's a piece of metal that's sized and shaped to absorb radio frequencies. And the size and the shape is a function of what frequencies you want to obtain. And the general rule of thumb is the more metal, the more signal. So bigger antennas in general will get you more signal if they're designed competently. The downside is nobody wants to mess around with a humongous antenna. That's why everybody, tries to get something small. And there's been a lot of work done. I mean, they've shrunk down what your cell phone antenna, used to have a kind that you pull out and talk on the phone, and now you don't even see the antennas because the antennas have gotten better and more sensitive. The radios have also gotten way more sensitive than they were a generation ago. So that's helped to keep some of the size down. But if you really want to get the most signal, you wind up with a larger antenna. That's why we have both indoor and outdoor antennas for customers, depending on what their needs are.
Now, we were all talking about signals and how the bars are almost meaningless, and how it's really about the frequency that you're getting, and then the reference signal receive power, reference signal receive quality, and the signal to noise ratio. And I found it surprising what you said was the most important to you.
Signal to noise ratio in no uncertain terms.
Wow, that is surprising. I was looking for power always, but
well, again, I'll use an analogy I've used with some customers in the past. If you think about a stereo or radio that you have that can go from 1 to 10 for the volume, and that would sort of represent the power that's coming out of the thing. At 1, it's very hard to hear. And at 10, it's easy to hear, but it's hard to make out the music because of all the distortion and just sort of too much because everything's being amplified, the noise and the signal. So what you really care about is that ratio of how much signal do I have versus how much noise, and what can you do to minimize it. And that's where some of the newer technologies like MIMO come into play. They're designed to help minimize the interference by electrically measuring it and sort of canceling it out. And if you think of kind of like a noise canceling headphone, that's kind of what MIMO does. It cancels out some of that background noise so that the radio can get more of the pure signal. So when we talk to customers, we ask them to focus on trying to maximize that signal to noise ratio. It's a positive number. It ranges from 0 to infinity, but typically you're going to see it in the low double digits. 10 to 20 is a great signal. Over 20, stop spending money because it's not going to get a lot better than that.
Yeah.
That's another great point. People often ask me, they're like, if I get an antenna, will it improve my signal dramatically? It's like, well, it's like getting a pair of glasses. Will they help you see better? Depends. Do you need glasses? So,
well, the other thing that a lot of customers ask us about is, how can I get more bars? I've got 3 bars. I want 5 bars. And the answer isn't really the bars. I mean, we talked about earlier the signal strength and how important it is or actually isn't, and things like signal quality, signal to noise. One of the basics is just putting speed test on and looking at the megabits you get. You may get 3 bars, but you're getting 200 down and 100 up. That's pretty good. It's for most people, and it depends on what the most power you can get out of the tower. So their tower, your tower may be able to do a gigabit, but their tower may be able to do 200. They're getting 200. So again, at the end of the day, the real measurement is something like speed test.
Yeah. The other thing that is not widely known about cellular equipment, particularly consumer cellular equipment, is that it has a built-in technology that's called automatic gain control. So it's designed to keep your device underneath the FCC power output limits, the radiated power limits. So as the signal environment is better in your space, the radio will actually reduce its output power because it doesn't need to be as loud. It doesn't need to send out as much energy. When you introduce antennas, that artificially can increase the appearance of that signal because it's been focused down. And what will happen is your radio will actually compensate and turn down. So it's a diminishing return. So, getting from 3 bars to 4 bars is one thing, 4 to 5 is another thing. Or if you're looking at the raw numbers, each additional dBm you're trying to increase, it gets harder and harder and harder to do that. And you wind up spending more and more money to some point where you just can't make it any better than that. And that's a requirement for every cellular radio that's been made in the last, 15, 20 years to have that gain control built in. And even the amplifiers, the external amplifiers, there was a big change in our industry a few years ago where they all had to implement this technology. So all the old ones are grandfathered, but you cannot buy one today that doesn't have that in it.
Interesting. All right. Well, I also found it interesting because someone asked me about, they wanted a better uplink. They wanted faster uplink scores, and they wanted to know if they could increase that gain. Well, obviously they can't. But what I didn't understand is that different bands, they're not all asynchronous. Uplink and downlink can be completely different by band. So you may actually want to band lock to a band 2 as opposed to, a different band, because that's going to have more uplink, and then so it may lower your download speed, but you may get it right back in upload speed.
Yeah, that's right. In each band, like band 2, band 61, band 71, whatever, the carriers have a series of frequencies, and it's broken down or called channels. And within those channels, they make the decision at the tower level how many of those are to be downlink and how many are to be uplink. And if you look at the specs for a band, you'll see that it'll say these frequencies are uplink frequencies, these are downlink frequencies, and they can allocate those. So they may choose, because they feel that most people here are just doing download stuff, that we're going to put 80% of the channels for download speeds and 20% for upload speeds. Other places it might be even. Although, frankly, we rarely see it even. It's usually biased towards download. They tend to have more capacity on the download side. There's not a lot of people are doing upload stuff.
Amazed by your comment earlier. We talked about cell towers being on the move, and how many of the providers, they don't actually own the tower, but they rent space on it. And as they look at the demographic that they're serving, they may choose to actually move the tower, or move their equipment. So the tower you were once pointing to may actually not be there anymore.
Correct. Well, the tower itself is, the physical real estate and the actual tower structure, whether that's a tree or a real tower, or, like Kevin described, some type of, architectural object where they mount antennas on, like the side of a building. That's usually fixed. But the carriers can choose where they lease space. And the guys who are in the tower business are kind of like, like apartment companies, in the sense that, they can rent to different cellular carriers. So basically, when a cellular carrier has an opportunity to move to a better location that may serve more people and allow them to, make their customers happier, they'll move their equipment from Tower A to Tower B. So the tower isn't moving physically, but the carrier's taking their equipment and going to another tower. And, sometimes it's additive. Sometimes they keep the old tower and add the new one, but many times they reposition equipment. And that's why if you have a directional antenna and you've been getting great signal pointing at Tower A, and suddenly your signal drops to either nothing or, it's very poor, odds are something like that's happened. So you want to look around, check Cell Mapper and, all the other guys, and you take a look and see if your carrier didn't move their equipment.
Yeah, it happens a lot in areas. I don't know what it's like. Silicon Valley may be built out, but here there's still a lot of growth where new subdivisions are being created all the time, and those people need coverage. And so sometimes they will reposition it to cover 2 subdivisions instead of 1 that was covering before, or something like that. Those kinds of things can happen. And then there's sort of the normal upgrade. They rented this space for their 4G service. Now they're rolling out 5G, and they decide, because 5G doesn't go as far, they need to move to different locations. And so it is dynamic. The cell towers are not there all the time.
Just really quickly, for rural areas, or I guess in general, there's 3 different types of antennas. We have the omnidirectional, and we have the directional, like the panels that you guys have that I've had a lot of success with. And then there's ones that are just line of sight focus, right? So more of your Yagi types.
Yeah, the Yagi or log periodic, dipole array is the technical name for them. And then there's an even more focused one, which is sort of grid-shaped, traditional dish-shaped thing. And those are not too popular. I mean, they aren't used very often unless you're really far away from a tower and really need to get that 20 plus mile kind of space.
They're also more popular in the higher frequencies.
Right. It's very hard. The dish would be very large to get low frequencies. That's one of the things the other thing that we didn't mention about, you talk about more metal, the lower the frequency, the larger the antenna tends to be. So if you have any friends that are doing ham radio or stuff, they got humongous antennas because they're down in the hundreds of megahertz range and not the gigahertz range.
That's right.
And
those are big antennas.
when you get into the high frequencies, up in the above 6 gigahertz, the antennas get really tiny. And when they get into the millimeter wave stuff, the antennas are chip sized. They're literally microscopic. So.
And as the frequency increases, it's easier to get gain. So at 600, it's harder to get gain out of an antenna than it is at, let's say, 3,800 megahertz, in the C band.
Okay. The other thing we were talking about, the Yagi antennas, we were talking about the 90 degrees between the two. I always thought that was the most powerful antenna. But what you were telling me was that the reason for the 90 degrees is just to get them to stop interfering with each other and allow them to be in close proximity with one another.
Correct.
Well, the issue is for MIMO. The way that MIMO works is it looks at it's multiple input, multiple output. So it's looking at the two input streams, in this case, coming in, and it's using that information to difference between the two to eliminate the interference and maximize the signal. If it gets two signals that are essentially identical, it can't really do its job. So it needs them to be independent. It needs them to be separate antennas, and antennas that are not designed to be MIMO antennas, they need to be physically separated so that you get distance. So you actually put them a minimum of roughly 2 feet apart or more. What you can do with directional antennas, because the beam is so narrow, is you can actually mount them at 90 degrees to each other, and that'll get you isolation. It's called phase isolation, and that's why we recommend doing that. Some people do it at 0 and 90. Other people do it at plus or minus 45. It doesn't matter. It's as long as they're 90 degrees to each other is what matters.
Yeah, no, that is interesting. I always assumed that they were somehow acting in concert, but what they're actually doing is trying not to interfere with one another because they're in such a close proximity.
Well, that's why you do it that way. When you get to 4x4 MIMO, then it's the same thing, but then an additional 2 rotated 90 degrees from that. So everybody's 45 from each other. So.
Yeah, if you didn't change the angle so that they're 45 to each other, total of 90, you would then space them 2 or 3 feet apart.
Which is what you do with Omni antennas. You have to separate Omni antennas. Now, we do make a 2x2 Omni-directional MIMO antenna. It was designed to be MIMO, and so the elements are electrically isolated from each other so they won't interfere. So it lets you do it in a single tube and in a single mount as opposed to the 2-mount.
That's like the Big Bertha that I have, right?
Yes, it's 12705M is our part number. But the antennas have to be designed for that. You can't just take two standard antennas and stick them next to each other. They will it's kind of like a microphone and an amplifier. You get them too close together and you get feedback. So that's what's going to happen. Because remember, these antennas are transmitting and receiving simultaneously effectively. They're multiplexed in, but they will interfere with each other.
So I pulled up Cell Mapper the other day, Open Signal, and I was able to see that there's so much. My area is so dynamic. The area is exploding with 5G. So there's new towers popping up all the time. The one that I was pointing at originally, 1.7 miles away, may not be the closest anymore. I'm thinking of putting up that omnidirectional antenna and seeing if I don't pull in better signal than I was before.
Yeah, well, as Jim mentioned earlier, the tower that's physically closest to you may not be the best one for you to use because it may be more heavily taxed. It may be at different frequencies. Again, there could be angular issues involved. So when we talk to customers about siting their antenna, a directional antenna, you do have to do kind of the sweep and say, what am I seeing here? You start with the physical map and say, I know there's a tower here, but see where the next two are. And you may actually get better service from one of those.
That's the big question in sales that we get is, well, I want to get the most signal, so I want it directional. And if you start talking to a customer about the issues that Kevin just mentioned, that the best tower may not be the one closest. That one may be overly taxed. With an Omni, if you set it up, the radio will pick the best tower. You don't have to worry about it. And the best tower today may be different than tomorrow. It actually may be different in 10 minutes. So having an omnidirectional antenna buys you the ability to let the radio select the best tower that it can see. The trade-off is with a directional antenna, you're kind of focusing a beam more or less. I mean, so, you don't see things on either side. So something behind you don't see. And that's the trade-off. So, again, getting a good omnidirectional like our 10 dB and, getting two of those in a MIMO configuration, it's hard to go wrong, except if you have to hit a tower that's extreme distance. Then, you want to look at directional antennas.
The way to think about it is think of them like a funnel. An omnidirectional, stuff comes in from all directions. When you get to a directional antenna like a panel antenna, it's coming in at what's called a beam width. So on ours, I believe it's 80 or 75 degrees. It's bringing in there. So what it's doing is essentially taking a signal from that angle and bringing that in. So the tighter the beam width, and that's when you get into the Yagis, you get into the 15 or 20 degree, and you get into the grids, which are like 5 degree kinds of things. It's a focus. So you're not creating anything. You're simply focusing it.
And the focus is somewhat expressed in the dB of gain.
That tied with the beam width. That's correct.
Right.
And again, one of the things that we talk to customers about, because again, it's a common misunderstanding, is what does the dBi of an antenna mean relative to the numbers that they see on the router? And the answer is it means absolutely nothing relative to those. Unfortunately, we engineers tend to use the same symbol, dB, for lots of things, because it means factor of 10 to us, but to the consumer, it gets confusing. The things that you see in your radio are power measurements. dBm is a power of measurements, M is for milliwatts. dBi is simply a unitless number, which is how good does this antenna focus signals relative to an ideal antenna, which is a perfect antenna, which does not exist. I mean, you can't build one. And so it's you can't say, well, I've got a 5 dBi antenna, so I should increase this value on my router by 5. It doesn't work that way at all. And that's, a lot of people get disappointed, or we get comments about, well, I didn't get the gain I expected. Well, I don't know how they can tell that from the information that they have.
So the question that we talked about earlier in the week that I thought was really interesting was about environmental factors, things that exist in the environment, and some of them are counterintuitive. We talked about rain. We don't get a lot of rain, but we did get some this year, which actually made up for a 7-year drought. We got a ton of rain. But I didn't really notice a huge difference, maybe some difference, but it was not dramatic at all. I understand that some types of trees and such can even cause more distractions.
Yeah, it depends again on the frequency. The resonant frequency of water is 2.4 gigahertz, which is what your microwave uses to heat up food. So if you're in the old Sprint 2.5 gigahertz, you're very close to that. So heavy atmosphere, water, rain, fog, those kinds of things can create that. At the lower frequencies, like 700, 600, it goes right through that stuff, so you should have little impact on it. Same thing at the very high frequencies. You'll see power dissipation, but the signal will still get through. It doesn't get totally absorbed.
Which frequencies are you talking about when you say higher?
Oh, we got up into like the C-band above 3 gigahertz.
Okay.
So everything for 5G until recently, 4G, recently was under 2.7 gigahertz, and they're just allocating now between 3 gigahertz and 6 gigahertz. Verizon and AT&T and T-Mobile are just starting to roll that kind of stuff out. I'm not sure there's a whole lot of towers out there that support it just yet, but the industry's trying to get ready for that. It's a good medium between speed and penetration. You get decent penetration, you get great speeds.
I really like what T-Mobile did. They took two mid bands and they aggregated them together and got the performance back that way, but they got the coverage with the mid band. So
yeah, they were. To be honest, they were pretty smart about what they did and how they acquired the frequencies. Verizon bought a whole lot of microwave frequencies, millimeter wave frequencies, and it's not really suitable for mobile applications. It's fine for point to point or that kind of thing, but it doesn't work so well for phones and cars. So.
$54 billion is what they spent with the FCC. T-Mobile spent $9 billion, which is a lot, but yeah.
And maybe we'll be surprised and they've got some secret technology that nobody knows about yet, but
it may pay off in a few years, but when they first bought it and they first rolled out the millimeter wave, Verizon's sort of poster child project, which was the Foxborough Stadium, they, I think, put 48 nodes in there, said, oh, we're going to cover it all, and people were finding dead zones, and if you went to the bathroom, there was a dead zone, and sometimes if you turned around in the right spot, dead zone.
Yeah, I mean, we were talking about towers, in the 600, 700, 800 megahertz range going 20 miles. When you get up into the millimeter waves, the 38 gigahertz and 42 gigahertz, you're talking about hundreds of yards of coverage. So, expect an access point on every other pole out on the street. So.
But huge amounts of speed and huge amounts of payload for the network operator. The network operator can serve, whatever 10x that they can in the lower bands, because the higher band offers that.
Yeah, the analogy that makes sense to me that I heard a long time ago was when you hear someone else's radio in traffic, oftentimes what you hear is the bass, because the lower frequencies, they penetrate things. The high frequencies, they're attenuated by the windows. They're attenuated by distance. They're attenuated by everything. But you hear the bass because that's the low frequency and that goes through anything.
If you think about it, what they use extremely low frequencies to send out the time signal. If you have one of those atomic clocks.
I do.
And the U.S. military uses extremely low frequencies to talk to submarines, so they can go around the world with those kinds of things.
They call it ULF, ultra low frequency. Yeah.
I have one of those atomic clocks, and I heard that it was picking up a signal from Denver.
Yeah, it is in Colorado. It's not Denver. It's where the U.S. Naval Observatory is out there, Colorado Springs, I think.
Interesting.
I'm not sure.
Yeah, well, it makes sense now that it takes such a long time when you hang it back on the wall because you replace the battery. It'll take
because it's only getting a few bytes of data a minute.
It takes a long time for it to finally do its thing.
And most of the clock apps, if I remember correctly, are midnight to 6 a.m. Eastern time. I mean, they're not transmitting all day long. It's only there's a certain nighttime nocturnal zone that they every hour they send out the update, and then your clock catches it.
So it's like a beacon.
Correct. And as Kevin said, at these low frequencies, they don't, they're not sending much information, but they don't have to, they just have to send the time. The big thing is on the clock, you have to pick your time zone because it doesn't know where you are. It's sending out a GMT type time.
I think in the future, I think they're going to be set by the GPS system, because that's, a lot easier. It doesn't go through the houses as well. So I guess maybe not, but your cell phone clock is an atomic clock essentially, because it's relaying from GPS to get its signal, and so is the cellular cell phone network. It uses GPS timing to keep everything in sync, so you can't get any more accurate than that.
I remember back in the day we used to set all the clocks, and you'd go around, and if you were really OCD, you tried to get them right down to the closest you could. But no one has to do that anymore. The clocks all set themselves.
Yep.
Mostly.
There are a few old ones.
Peter, you brought up a topic about water, which is something, again, that's counterintuitive. We've run into customers that have difficulty transmitting signal across bodies of water, particularly calm lakes. And it has to do with the way that signals bounce off the surface of water at certain frequencies. And so we've had customers that say, I can see the tower, it's on the other side of the lake, and I'm having trouble getting connection to it. And it's because that normally that signal would be absorbed into the ground and wouldn't bother you, but when it hits the water and bounces back up, it can create some interference. So sometimes we have to get the the antennas even higher, or you have to move them to different locations to get around that problem. But it's counterintuitive that water would be a problem.
Yeah, you're thinking I have no obstructions in front of me because
Right.
it's a smooth lake. But I think, Jim, you were telling me a story about pine needles and how they were just the wrong size or something.
Well, I think that dovetails into the water thing. Kevin and I had a project many years ago involving signals around the city of Pittsburgh, and we ran into a location that there were trees in between the two. It was point to point, but it was actually a big mesh network. But the 2 points that had to connect had trees in the middle, pine trees. And the signal was pretty good when the weather was dry and just normal, winter, whatever, summer. But when it was raining and the trees were wet, the signal dropped drastically. Sometimes we even lost connection. That's how, we'd receive a call. Hey, there's nothing there. And again, if you're in this business, you'll come across things like that where the trees or whatever, when they're wet, create a problem. Not for everybody, but in certain locations.
And that was a 2.4 gigahertz application, so
Yes.
it was very sensitive to that.
That is interesting. You were saying 2.6 megahertz is the same as
2.4 gigahertz.
2.4.
2.4 gigahertz. Okay. Because I was like, are we, with our Wi-Fi, are we irradiating ourselves? But no.
Yes. Yes. Your 2.4 gig, yes, you are. But the power output is so incredibly low that it's deemed to be safe.
We're cooking ourselves slowly.
The same frequencies that are using on your microwave. And there's lots of, stories out there where people are like, my Wi-Fi is great, and then I microwave something and it won't work. And it's because microwave is leaking and it's interfering.
Get a new microwave.
There are a number of articles out there, where not to put your home gateway router, and don't put it on the microwave. Yeah.
Wow. Yeah.
Yeah. But people do it.
All right. I think we got everything we need, guys. I thank you so much for your time. It's been
no problem.
You're very welcome.
Been,
Okay.
All right.
Thanks so much.
Talk to you soon.
Okay.
Bye-bye.
Have a good night.
Bye-bye.